So today we are considering the wave equation, the one-dimensional wave equation. So the equation writes the second derivative with respect to t equals the second derivative with respect to x. You need an initial condition u and ut, and then here so the domain, the spatial domain is 0, 1, and you need to fix, for example, so this is Dirichlet condition. So you fix as 0 and 1, you fix 0. So physically, it means that the string doesn't move at the ends. Okay, so what we gonna do is we are trying to set a framework with a domain, with an operator A and the right domain, and try to see if our operator generates a C0 semigroup. Okay, so yeah, so first, since what we've done, we have this theorem which says, in fact, if A generates a semigroup, then the semigroup satisfies the differential equation. So it satisfies S prime, or with prime the derivative with respect to t equals AS of t. But here we have the second derivative. So the first thing that I propose to you is to put that equation in order 1, meaning that I don't want here a second derivative, I want just the first derivative. So try to put this equation in a form where we have only one derivative, not the derivative of order 1. All right, so first thing to do is to transform this equation 1 into a first order equation with respect to the time. So in order to do that classically, we will set ut equals v, and then I obtain vt equals uxx. Okay, and so now so to do what we did before, I would like to write that uv, and I take the derivative with respect to the time, let's say prime, equals a uv. So if I want to obtain that, what is my a? So with a, it associated at uv. So I didn't specify here what is my Banach space, but just do it first. We're doing it together. We're thinking about it. So my operator here will be so v and uxx. Okay, so what is our space X now? So our space X will be, so in the space X, I need to include the boundary conditions. First, And then in the domain, I need that to be well defined. So let's say we want to work with L2. I want to work with L2, but I need to include my initial my boundary conditions. And so you see here, you have the boundary condition. So what will my space X will be? X equals H1 node. So the boundary conditions, the J-play boundary conditions appear here. So this is where U lives. And here, I will choose V, L2. Okay, but now I want this one to be well defined. So I want that the second derivative with respect to X belong to L2. So I mean, it means I need H2. Well, so the derivatives are taken, of course, in the sense of distributions. So finally, my operator is like this at UV. It associates V UXX, and so GA is, so it's H10, and I need to take the intersection with H2 times for V I only need L2, right? And X is HN001 times L201. Okay, so with that in mind, we want to do the same thing as before. So we want to prove that A generates a C0 semigroup of generates a C0 semigroup. And so how can I do that? So so again, we want to apply, we will apply the Yoshida theorem. And so to do that, if you remember, what I need to do is to study the operator lambda identity minus A for positive lambda, and in fact what I want is to see if this operator is well defined. So by analogy with so as we did for the heat equation, what we need to do first is to prove that the resolvent operator here, lambda identity minus A minus 1, first is well defined on X. So to do that first, we need to consider, so we look at lambda identity minus A applied to UV equals, let's say, FG. And so here, so for every F G belonging to, do I have a solution for that? For every fixed fg, do I have a solution for that? So how does this work? So I will have that. So I recall that AUV is VUXX. So if I look at lambda identity minus AUV, I will get lambda U minus V equals U, and lambda V minus UXX. So it's not U, of course it's F. All right, so now the question is, for example, can I solve 2? Yeah, so there's a good proposition in the chat. So let's do the details on that. So yeah, so well, you can see that if you multiply the first equation here in the system 2, if you multiply the first equation here by lambda, and then you sum up with the second equation, what do you obtain? So you multiply the first equation by lambda, and you sum up with the second equation. What do you obtain? So what do we obtain? We obtain, so multiplying, no, it doesn't feel correct. That multiplying the first equation into by lambda and summing up with the second equation, we obtain, so we obtain lambda u square, so minus lambda v plus lambda v u, sorry, minus lambda v plus lambda v will cancel, and it remains minus uxx equals g. So I obtain lambda square u minus uxx equals lambda f plus g. All right, what can I do with that? So what can I do with that? So then what? Then we already worked on this equation because here I have so lambda square identity minus a u, but with a equals uxx. So that's what we did with the heat equation. And so for that, we have an explicit solution of u of x. All right. Yeah, so, but this work, we already did it when we studied the heat equation. And so we have an explicit solution by just taking the formula obtained for the heat equation and replacing lambda by lambda square. And so we got this formula. here there's a H node, which is defined as that, and then you can take your first equation here in 3.6, and this gives you V equals lambda U plus F. So what does it mean? It means that our resolvent operator, lambda identity minus A minus 1, is well defined. For each FG in X, I got a solution in GA, in fact. Right. Are the Dirichlet boundary conditions well defined? Yes, because in this equation, I have taken in account the Dirichlet boundary conditions. When I write that, so we did that last time. So here, there's a bunch of easy computations, but they are quite a few. And to find this, I used the Dirichlet boundary condition. So thanks for the question. Okay, and next, yes, you can write V equals lambda U minus F here. So lambda identity minus A minus 1 is well defined in all X. Okay, so now I need to prove that our operator is bounded and that I have a bound in the operator norm of 1 divided by lambda. So if I got that, then we're done, and the wave equation generates a C0 semigroup of contractions. Okay, so next, let us remark that in fact X is we endo X with a scalar product. So for every so Z1, Z2 in X, we define the scalar product so Z1 equals U1 V1 and Z2 equals U2 V2. So we define the following scalar product by the integral between 0 and 1 of U. So here I take the derivative with respect to X. Let's say that. Plus the integral between 0 and 1 of V1 V2. Okay, and so with this norm, this product scalar and the associated norm, X is a Banach space. Okay, so all right. So now, can you find an estimate for the operator norm of the resolvent operator? So can you bound the norm of lambda identity minus A? Minus 1. And in fact, I want that. So can we do that? So now what we have is, so we have that lambda u minus v equals f, and lambda v minus u x equals g. Yeah, so I want to relate this equality with the product scalar and with the product scalar in order to get this norm, and it's close with what we did last week. So here, of course, this equation is lambda identity minus a uv equals fg. And so I will take the scalar product on both sides here. So what I'm going to do is I will look at this quantity, and this is equal to fg. So let's write that. Okay, so we are going to write that. So I recall that. So this is the same that writing lambda u minus v minus u x, and I want the product scalar with uv equals fg product scalar with uv. So I recall that the product scalar is I need to take, so lambda u minus v prime integral times prime plus integral v minus u, so x it's u second v us, but yeah, forgot the lambda here. Lambda v all right, equals integral between 0 and 1 of f prime u prime plus integral between 0 and 1 of gv. All right, so now, okay, here with this term, I will use an integration by part. Okay, so here I know that thanks to the Dirichlet boundary condition, I have that 0,1 u second v equals minus 0,1 u prime v prime. So here, those terms and those terms will cancel. So I will obtain, I will write it nicer in the next slide, but here I will get, so lambda 0,1 u prime square plus lambda 0,1 v square equals 0,1 f prime u prime plus 0,1 gv. So just let me write that in the next slide. So we obtain that u prime square plus equals all right. What's that? Forgot the lambda also. Okay, here, what's that? This is lambda uv uv. This is yeah, I did that, but this is I did nothing here. All right, but by definition of the scalar product, this is nothing but the norm of uv in x square. Okay. And so here is the same. Okay, now I use Cauchy-Schwarz inequality here. So this is less than the norm of fg times the norm of uv in x. So finally, I got that lambda uv in x is less than the norm of fg in x. Okay, but uv is exactly lambda identity minus a minus 1 fg. Okay, so if I divide by the norm of fg in the other side, and I take the sup, I obtain that the norm of lambda identity minus I minus 1 is less than 1 divided by lambda. Okay, so that's what we wanted. So we just proved that our operator A generates a C0 semigroup, and the S of t, this S of t, is solution of the wave equation.